So let's talk about what this graph might look like. If we did this experiment with Wally, we know that we applied 155 newtons of force. So let's just identify where that is on this graph. So let's just say that right there is 155 newtons right there. That's what the force of the extinguisher is right there. So now, if I'm applying that in this lab, he's not really changing the amount of force as he's moving. He's just applying one constant force the entire time, which is causing the force diagram to become unbalanced, which is causing him to constantly accelerate or pick up his velocity. So in this case, it's basically a constant amount of force applied until that 34 meters. Let me identify where 34 meters is. We'll type it in right down here. So that's the displacement of 34 meters right there. So then what this graph would look like is something like this, where I'm showing a constant 155 Newton force for 34 meters. Now, you may be thinking, that's interesting. Well, let's talk about something even more interesting. We saw a graph at the beginning of the semester, slightly differently labeled, but instead of having this appear as F of the extinguisher, we called that F of spring, and we had the spring displacement down here, and we had a graph that looked like, let me draw it like down here, that, and let me change the color to blue. We had a graph that looked like that. And if you remember, this was the very first way that we quantified energy back in Hooke's Law, Lab P.8.2. And when we did that, we found that when we made a graph like this, we found the area under the curve, and this area right here represented the amount of elastic energy that was present in the spring. Well, in this same situation here, the area of a force versus displacement graph can be thought of as a area under the curve, or the amount of energy that is being added to the system, or the amount of work. So therefore, if I wanted to find the amount of work that was done in this case, then I would simply find the area of this shape, and that shape in this case is a good old-fashioned rectangle, going from there to there with a base and a height. And how do you find the amount of area of a rectangle? Well, you would just simply say that the work, or the amount of energy added, is equal to the height, which is 155 newtons, times 34 meters. And then you would multiply those, and that would be your amount of work. And if you're like, well, wait a minute, the units don't add up. Well, let's think about that. When you take newtons times meters, that's the same thing as a joule. So therefore, we will indeed get energy units when we find the area under this curve. So the important thing to realize is this. Work can be found by taking the force times the displacement. However, it's important to know that the force has to be constant in order for you to take the force times the displacement. If the force is not constant, then that's not going to work. The easiest way to think about it is as the area under the curve of a force versus displacement graph.